We're back with example 5.7 on page 152 of our text, second edition, Exploring Creation with Chemistry. This is another one of our mole questions. This time we're going to be given a specific number of moles of pure ammonium, and we want to know, to be able to determine what that mass is. So first we have to have N, which is nitrogen. Ammonium is composed of one atom of nitrogen and 3 atoms of hydrogen. So if you look at nitrogen on your periodic table of the elements, that is element number 7, nitrogen has an atomic mass of 14.0. Hydrogen, which is element number 1, has an atomic mass, as you recall, of 1.01. However, do we only have one hydrogen atom in this? No. We have 3 hydrogen atoms, so we have to multiply that by 3. So the atomic mass of pure ammonia is 14.0 plus 1.01 times 3, 3.03. 17.03 atomic mass units in 1 molecule of ammonia. Well, we don't know anything yet about molecules. We know moles, and we want to find out how many grams, what the mass is of 12.331 moles. Well, what is a mole? 1 mole is the number of elements, the number of molecules of a compound that has the same mass in grams as the mass of that compound in atomic mass units. So the mass of ammonia, 17.03 AMUs. That makes up 1 mole. So if we have 17.03 grams of ammonia, that is going to be the mass of 1 mole. So let me show you what we've got here. .03 is equal to 1 mole. 17.30 grams. How many grams of ammonia are there in 12.331 moles? Well, we don't know that yet, but we do know that that 1 mole of ammonia has 17.03 grams. So our moles are going to cancel out. So the number of grams of ammonia that we have in this sample is going to be 12.331 times 17.03 grams to tell us how many grams of this stuff we have. We get our calculator out. We're going to multiply 12.331 times 17.03, and we are going to end up with 209.996. Okay. How many significant figures are we allowed to have? We're only allowed to have 4 significant figures because we have 17.03. Well, 1 2, 3, 4. But if we make that, that's going to round to 0, which makes that round to 0, which ends up with 210, which only has 2 significant figures. So what we're going to have to do is use scientific notation. 2.000 times 10 to what? 1, 2, times 10 to the second, times 10 to the second grams is the weight of 12.331 moles of sodium. So if you look in your book, okay, I said 2,000, this rounds, it's actually 2.100. Now we have 4 significant figures. Why are we not allowed to do that for the number of significant figures? Okay, the reason is this. I said when we were adding these, and this is good to have this on the video to figure out what in the world went wrong. I would give you this, okay? But what we're actually looking for is we had 14.0 plus 3.03. When you're adding, we can't make this any more precise than our least precise number, so we didn't really have 17.03 grams. We couldn't use that. It was 17.0 grams, which means that we can only have 3 significant figures in our solution. So we have 209.996. We try to round that. That's going to become 210, isn't it? Well, you can't use 210 grams because it only has two significant figures in it. So rather than write 210 grams, we're going to convert that into scientific notation. 210 can be written as 2.10 times 10 squared grams. 2.10 has 3 significant figures. Multiply that by 100, and that's the same as 210 grams. So that's how we came up with that answer. Now let's go ahead and look at page 152. This is on your own problem, 5.9. And we'll go ahead and step through this one. .9, page 152. This is on your own. On your own. What is the mass of a NO3 sample if it contains 0.23 moles? So we want to find the mass of a find the mass of a sample of NO3 that contains 0.23 moles. 0.23 moles. How many significant figures do we have here? That's right, we only have 2 significant figures. It's precise to the hundredths. So we have to figure out the mass in 1 mole first. The way we do this is what is the atomic mass units for, or the atomic mass in AMUs of nitrogen, 14.0. Oxygen is 16. So we have 1 nitrogen, we have 3 oxygen, so that's 14.0, 3 times 6 is 48.0, which gives us 62.0 is the atomic mass of one molecule of NO3 in AMUs. So if we take 62.0 grams, that's going to be the mass in grams that we need for 1 mole of NO3. Okay? 1 mole is 62.0 grams. Okay? Now we're going to go ahead and erase this. If 62.0 grams of NO3 is 1 mole, then how much is 0.23 moles? 0.23 moles of the sodium. All we have to do is multiply 62.0 times 0.23. 62.0 times 0.23. That gives us 14.26 grams. How many significant figures do we have? 2. So that's going to become 14 grams of NO3 are contained in 0.23 moles of that compound. So let's go ahead and look back at the answers to the on your own problems, and hopefully I'm right. 14 grams of NO3. 14 grams of NO3, that's all we're doing with this. Now what can we do? And I know you're thinking, man, are we not ever going to get done with Module 5? Okay, this says using the mole concept in chemical equations. This is page 153, and this is really important here. This says the real importance of the mole concept at the top of the page is revealed when you look at how it relates Hello.